Hi everybody, it's Jim Corkins and welcome to our physics class again. We are in 5.3 and this is the work energy theorem. This is where we see how those non-conservative forces affect our energy equations. Okay? If you haven't started the reading, please do so. We are going to be reading chapter 7 in all the books. All right? Now, I wanted to start with something funny that for anybody that thinks that you can't get, it's difficult to get a PhD. Somebody got a PhD from studying rats, and they found out when rats giggle when they get tickled, and they'll actually seek out the hands. So if you get a chance, watch that video. It's adorable, and they have ultrasonic laughs, all right? And another bit of research, I have no idea why I'm talking about this now. It's just I'm weird. Okay, anyways, I just think it's funny. Somebody else taught rats how to drive little tiny cars. So they drive around and they get little treats and stuff like that, and they're actually pretty good at going through obstacle courses. But the funny part is those rats are actually laughing during the time that they're driving their little carts around. So I'm just saying it's actually really interesting and adorable, but research can be done across a lot of different spectrums. And so this research has helped us understand animals a lot more, and there are parts of their brain, especially with rats, that get activated during laughing and stuff are not too different from the parts of our brain that get activated when we're having a good time. Anyways, moving right along. So we are going to be using this as our procedure for this same procedure we've been working on for this whole time. We're going to write our equations. Our initial energy plus or minus work is equal to the final energy. Then we'll list out our three different, our kinetic and potential energies, have our work in the center, and then list out those energies again in the end. And we'll have a list of those energies, but also what is causing them: motion, height, springs, and outside force or friction. We're also going to do little mini force diagrams just to help us double check regarding the work. If there's any outside work or forces that are going in the direction of motion, then likely there's going to be an outside non-conservative work function involved in our equations. Anyways, let's get moving. All right. Again, I don't know why I put this out there twice. That's weird. Moving right along. If you haven't downloaded this or started writing this out, this is our list of equations. And so since our problems are now going to be using any of the contact forces that are non-conservative forces, I do want to just do a quick reminder of this, okay, of what work is. Now, work, again, is positive and negative work, again, is if we have a displacement vector, which is a velocity vector. We have a displacement vector to the right, which is basically a velocity vector. And we have a force vector pointing in the same direction. Which is basically an acceleration vector. So when those forces, vectors are pointing in the same direction, either both to the left or both to the right, what that means is we are speeding up, okay? And if you are speeding up, again, then you are adding energy to the system. Right? Something is causing you to speed up. So when somebody's pushing you to the right and you're moving to the right, you're going to be speeding up. And if you're moving to the left and somebody begins pushing you to the left, you will be speeding up. In other words, that is called positive work. since work is equal to force times displacement, right here, you have a negative force and a negative displacement, that's positive work. If you have a positive force and a positive displacement, that's also positive work. You're adding energy to the system. So positive work means adding energy. So in other words, let's say you weren't moving initially, so you had no energy, and then you begin moving and you end up with a final kinetic energy that is 6 joules. All right, so you have a final kinetic energy that is 6 joules. So again, the slope of this is power. So that's power, and that's positive in this case. And if this slope is positive, then work is being added into the system. So work is coming in and adding energy to the system, positive power. Okay. Now, if you're moving to the right, but somebody's pushing you to the left, or you're moving left and somebody's pushing you to the right, that would be slowing down. So this is speed up. This is slowing down, which means your final velocity is less than your initial velocity. And so you have a negative force times, you have a positive force times a negative displacement. So negative times positive, that's going to be a negative work, right? So in both cases, this is a negative work. Your energy is being taken away from the system. So energy loss of energy. That's what negative work means. So energy is being pulled from the system. So in other words, you start out with 8 joules of energy, and you end up with 0 joules of energy. So that's a negative slope, which means energy is leaving the system. Okay. All right. Again, if there's no change in energy, that means power is 0. That means work is 0. So no energy is being added or taken away. So this would be conservation of energy. Okay, so just want to review work again. And also remember too that the force and displacement have to be in the same direction for work to be added to the system, for energy to be added to the system. All right, let's try our first problem. Here we go. So this is going to be close to what you're going to be doing in your tutorials. Okay. These are very simple. They're not too difficult, but I'm going to ask you to do a lot. And well, not a lot. I mean, it's not that hard. You'll see. They're actually kind of interesting. Hopefully this will get you thinking about things. All right. So here we go. In this situation, you have a box that's moving at a constant velocity across the floor, and it's not changing its velocity. Its initial velocity is positive 2 meters per second, and its final velocity is positive 2 meters per second. So its velocity is unchanging. Okay. So let's, what we're going to do is we're going to list out our energies and list out this equation, list out all these equations. Let's do our little force diagram first. So this is an object moving across a frictionless floor at a constant velocity. Okay, so the first thing we do is we write it's got a mass times gravity, which in this case is negative mg, which is going to be negative 2 kilograms times 9.8 meters per second squared. So that's going to be its weight. And then since it's on a surface, now what's physically touching it is a surface, and it has a normal force pointing up. Okay, cool. Now, since it's on a surface, we normally would have friction, but in this case, it says frictionless. Now, we know it's moving to the right at a constant velocity, but it is not speeding up or slowing down. And so its velocity in the y directions are 0. So notice that there are no forces that are parallel to the direction of motion, right? If there was a force pointed to the right, and the velocity vector is pointed to the left or to the right, then we'd have to start thinking about work. So this is why it's important to do a force diagram when we analyze energies. All right, now let's take a look at the situation. Initially, the object's moving, and it's 2 kilograms. And then finally, the object's moving at 2 kilograms, and it's 2 kilograms. So initially, it's moving. Its height on the ground is 0, and no springs are touching it. Now let's look at the final energy. It is moving. Its height is 0, and no springs are touching it. Now, when it talk about work, do you see any forces that are pointed left or right, or can you think of any forces that are physically touching it that are parallel to the direction of motion? No. So there's no work. So what we have is the initial kinetic energy is equal to the final kinetic energy, right? So 1/2 mvi squared equals 1/2 mvf squared. And I'm leading into something, so just bear with me. So 2 kilograms times 2 meters per second that we're going to square, and this is equal to 1/2 2 kilograms times 2 meters per second that we're going to square. So this is going to end up being 4 joules, and this is going to end up being 4 joules. Okay. Now, looking at this, here we go. Let's look at the energy. And over a 6-second time frame, it started at 4 joules and it ended at 4 joules. So if we look at this, you can see the power is equal to 0, the slope is equal to 0, so no work is being added or taken away, right? Which we totally already knew. And in the direction of motion, so this force is in the direction of motion, it has no forces in the direction of motion over all 4 seconds, or 6 seconds. So there are no external forces acting on it, and no energy is acting on this or being taken away. So this is our lead-in, okay? All right, let's do the same thing, but now we will be dealing with energy, or with a work function, okay? So suppose we started out right here. Now, the object's not moving, and then something happens, and it's now moving at 2 meters per second, and it's a 2 kilogram box, same situation, 2 kilogram box, and it's been pulled from here to here over a distance of 2 meters. Somebody pulled it from here to here, and then they let it go, and it's now moving at 2 meters per second. Okay, and so they're asking us to figure out the force of the pull. We're supposed to complete this force versus displacement, the energy versus time, and a force diagram. So let's go ahead and try this one out. Let's start with the force diagram. So let's do the force diagram as it's being pulled. So you have negative mg, which is going to be equal to negative 2 kilograms times 9.8 meters per second squared. Okay, it's touching a surface, so it's got a normal force pointing in the positive y direction, and it looks like a force acted on it, which is probably going to be in the direction of motion. So a force would have had to act on it in the direction of motion. I'm assuming it's moving to the right because it says it is in this picture. So this force is to the right. It could be up and to the right, but we'll just say it's to the right for right now. And it looks like it was not moving, but now it is moving, so that means it's speeding up in the x direction and not doing anything in the y direction. Okay? All right. Now, let's do our energy first before we do these two graphs. All right? Because these graphs are going to be helpful. All right. Now, kinetic energy-wise, it starts out not moving. Its potential energy due to gravity is 0 and no springs are touching it. Let's move on to the final energy. It is moving in the end. The potential, it still has none of the potential energies. Now, if you have a situation where there's no energies in the beginning, but there are some energies at the end, there has to be work. And since this is positive here, this has to be positive, because you can't have a negative W equal a positive K. So what you're going to have is a positive work, and that's going to be equal to our final kinetic energy. Okay? Now, our final kinetic energy is 1/2. Okay, this work is going to be force times the displacement. Okay? Force times the displacement in the x direction. And kinetic energy is 1/2 mv final squared. Let's go ahead and solve for what we need to solve for here. So this is going to be 1/2, and it's 2 kilograms times 2 meters per second that we're going to square, divided by 2 meters. Okay, so this is going to be 4, so 2 divided by 2 is just 1, 2 squared is 4, 4 divided by 2 is going to be 2. So 2 newtons of force. Okay. Cool. All right. So we know now that that force that caused it to speed up had to be 2 newtons acting on it for a distance of 2 meters. Okay? So in this problem, we were assuming it was a constant force. So this force of 2 newtons was working over a distance of 2 meters. So you got 2 newtons of force working over a distance of 2 meters. Now the slope of this line, I'm not sure if that's very useful here. At least right now I can't think of it. But the area underneath this line is important. Okay, so if we look at the area underneath this line, I'm seeing a rectangle, and so that is a positive 2 newtons rectangle times 2 meters. Okay, now this area right here, that is work. That is positive 4 joules of work. That is this F dot delta X. Okay, so as long as we have a constant force acting on this over a distance of 2 meters, you're going to have a rectangle kind of problem. But if that force was not constant, right here, we're assuming in this case a force is constant. But if that force is not constant, you could get a diagonal line, which means you'd be getting a triangle. All right. We'll come back to this, but I want to talk a little bit more about that area and do a little bit of calculus there. Energy-wise, well, we need to plot energy versus time. Now, we don't know how long it took for it to speed up that distance. Okay, but we could figure it out, right? Velocity is equal to displacement over time, right? Not that big of a deal. And so time is going to be equal to displacement over velocity, change in velocity, I should say. They should have a delta in front of it. And so that displacement is 2 meters. The change in velocity is going to be 2 meters per second. And so what you get is 1 second. So this energy goes from 0. So this energy, which we figured out that this work right here from this is going to be equal to positive 4 joules, which means the final kinetic energy after you let it go and it's now moving is going to be moving at 4 joules, right? So it started out with no energy, and then over the period of 1 second, actually let's call this 1 second. It'll be easier to make it. It'll make more sense here. It started out with no energy, and it ended at 1 second with this energy right there. And so if you look at that slope of that line, that is going to be power. The slope of this line is power, which is the amount of energy used, which will be positive 4 joules over the period of 1 second. So this is informative because, again, that slope is positive, and if you have a positive power, then what that means is you're adding energy to the system. Energy is coming from outside, and you're adding energy to the system, right? And that force is what added that energy. Okay? So pretty cool problem. All right. Now back to this force versus displacement. You may have diagonals in here, and in that case you're going to have to integrate. So a better definition of work is whatever that function of force is times displacement, right? And so in this case, if we look at that function, it started at positive 2 newtons. Its slope, and we got to go over a period from 0 to 2 meters. So the slope of this line is 0. So I'm going to do a little bit of calculus here. So that slope is 0, and that would be newtons per meter times x plus 2 newtons dx, right? So this is that predictive line for horizontal right there. And then what you get is 0 to 2 meters, and you have 2 newtons dx, which means when you integrate, you're going to have 2 newtons times x that you're going to put in 0 to 2 meters, and we get 2 newtons times 2 meters. So that's just positive 4. Right? So that's another way to do it. I say do whatever is best, unless you're asked to actually integrate, do that. But otherwise, just look at it as a triangle or a rectangle. Okay? Use your calculus to just make sure to double check your work. All right. Now, so that's a problem where those two problems, you have no energy change. Okay, so that means no outside forces, so power is 0. Here, you had energy being added to the system. Well, again, friction, specifically kinetic friction, is going to always consume your kinetic energy. So kinetic friction consumes your kinetic energy, right? So if you push an object, you have a box, you give it a nice shove, do a little bit of work over a distance, give it a shove, and so now it's moving at a velocity greater than 0. And then it slides some distance, and now its velocity is equal to 0, right? So in other words, it was moving to the right. Well, we learned from forces that if an object is moving to the right, then its kinetic friction has to be pointed opposite that direction. Okay? Well, that means that velocity vector, which is kind of your displacement vector, and this right here is your negative force vector, right? Well, your force and displacement in opposite directions. You have a negative force vector times your displacement vector. That's positive. And what happens is you're going to have a negative times positive, which is a negative. And so what that means is that this is a negative work. It's going to consume your energy. It's pulling energy from the system. Okay? Let's see how to work with this now. All right? So same problem. Sorry about that. I went to a different slide. It's a similar problem, but now we're dealing with kinetic energy. In this case, the object is moving, and then it hits a patch of rough ground, and that patch of rough ground is across a distance of 2 meters, which brings it to a stop. So it's moving at 2 meters per second, and then it comes to a stop over a distance of 2 meters. Okay? So we write our equations, and let's go ahead and do our force diagram. Again, this is important, so you don't have to write, you can just put mg, you don't have to actually put the numbers in. So this is while the force is acting on it. So let's go ahead, and you've got a normal force physically. You have a normal force holding it up, okay? And that's the only thing touching the object. So mg force down, and then what's physically touching it is a surface, and the normal force is pointing up. Now, we know it's moving to the right, but it's slowing down, okay? Which means, and since there's the only force acting on it is the surface, that means there's a friction force pointed opposite the direction of motion, which is going to be negative mu sub k times the normal force. Okay? Now, this is important that we note this, again, just like the last problem, because if the object's moving in this direction, we've just noted a vector that is pointing parallel to it. So that, and since this is a non-conservative force, that means this is going to be a work problem, right? In fact, since it's moving to the right, you got a positive displacement times a negative mu sub k times the normal force, you're going to have a negative work. That's why it's going to be negative. It's consuming energy. All right, let's go ahead and start here. So you write out your equations. Is it moving in the beginning? Yes. It has no potential energies because it's on the ground. In the end, it comes to a stop, and it still has none of those potential energies. So here is our problem, okay? We have an initial kinetic energy, and we have this work function, and you could just leave it as positive if you want, is equal to 0, right? Or you could put the negative in front. I'll show you what I mean in a second. So when you put in 1/2 mv squared, that work function, which is a positive w, well, we're now going to go ahead and look at our vectors. Well, it's got a negative friction vector pointed to the left times a displacement vector. Since it's moving to the right, its displacement is going to be to the right, so which is a positive displacement vector. And that whole thing is equal to 0. If you didn't want to write it that way, you could just assume, well, instead of writing that way, I'm just going to put the negative in front, and then this will just be mu sub k times the normal force times delta x. All right? So that's why this is a plus or minus. I put a plus or minus in there to remind you that work can be positive or negative. But if we're continuing on doing it this way, let the vectors tell you what's going on. And again, this is a vector, and this guy is a vector. Okay, those forces are vectors. Okay, now what we have is 1/2 the mass, which is 2 kilograms, times the velocity, which is going to be 2 meters per second, that we're going to square. We're going to go plus, well, actually, I'm going to just pull that negative out. So this negative times negative, negative. So this is going to be a negative mu sub k. The normal force, we don't know what that is. I'm going to leave that there. But we do know the displacement is times delta x, which is equal to 0. Now, right now, we're asked to solve for mu sub k, but we have another unknown. And so what I could say is this. Here's what I mean. If you ever don't know what to do, just start solving for some stuff. Okay, and I should put in 2 meters right here. Just solve for the variable that you need to solve for. Okay, and here's what I'm saying. So this is going to be 4 joules, and let's subtract this onto the other side. So then we have add it to the other side. So then we have a positive mu sub k times the normal force times a positive 2 meters. Now we're going to divide both sides by, we want to solve for mu sub k, we're going to divide both sides by f sub n times 2. So if you're ever stuck algebraically, just solve for what you need to solve for, and it'll show you what variables you need to figure out. In this case, we can't solve for this because we don't know what that normal force is. Well, how do we figure out the normal force? Well, right over here. So we know this object is going to be negative 2 kilograms times 9.8 meters per second squared. So that's going to be roughly negative 19.6 newtons. So the weight of the object is 19.6. Now, from the other reason why force diagrams are important, and you should do this selectively if you need to, is when you sum the forces in the x and y direction, we don't need to do it in the x direction, but in the y direction, it's useful to have this already written because you could just quickly figure out that this 19.6 newtons, that's going to be equal to the mass, which is 2 kilograms, times the acceleration in the y direction, which is 0 meters per second squared. So what we've figured out is that this normal force minus 19.6 is equal to 0, so the normal force is equal to 19.6 newtons. So another reason why I do a force diagram, other than analyzing your energy, seeing if there is an outside force for work, is you might need it to actually solve for something. In this case, with friction, you have to figure out the normal force. So now that we have that, we're going to put that in. So this is going to be 19.6 newtons. So we just plug this little guy into here. Times 2 meters. And so that mu sub k that's going to be 4 divided by 2, so it's going to be 2 divided by 19.6. It's going to be like 10, a tenth-ish. 0.10, yeah, it's a tenth. So this is 0.10. Okay. So it's handy to have all that ready. Now, let's go up and take a look at this. So this force, let's figure out what the force was. The friction force. So in this case, the friction force, which is going to be equal to mu sub k times the normal force. So we need to plot force versus distance, right? So this mu sub k is 0.10, and we're going to multiply that by 19.6 newtons. And so that's basically, I'm going to move that to the right, so that's basically 1.96 newtons, which is, we'll just call that 2. Like it's about 2 newtons, right? And so when we're plotting this on the force versus distance, okay, it went a distance 2 meters, and that force friction is a constant force, which is right here, and it looks really similar right here. So what we could find out is, see that work, that is our area. So that's 2 newtons of force across 2 meters. So that is going to be 4. Oops. I forgot. This is in the negative direction. Very tricky. The vector is important. So this, it should be negative. It should be negative right there. Caught myself. So this is a negative 2 newtons of force. It's pointing to the left over a distance of 2 meters. And so this area right here is going to be work, which is going to be negative 2 newtons times 2 meters. So that work is going to be equal to negative 4 joules. Okay. All right. Now, if we look at this on an energy versus time graph, it was moving at 2 meters per second. I just want to point out this is below the line, so this is a negative work. So back to this real quick. So that's a negative 4 joules. That means that energy is being taken out of the system, right? Now, on an energy versus time here, before we could do this, we have to figure out how long it took for it to go from 2 meters per second to 0 across a distance of 2 meters. And what we found out is delta t is equal to delta x over delta v. Delta v over delta x, delta t, and then you get this, which is going to be 2 meters distance, and that's going to be 2 meters per second. And what we get is 1 second, right? So again, let's call this 1 second right here, right? Well, it started out moving at 4 joules. So it had 4 joules, right? Kinetic energy was 1/2 times 2 kilograms times 2 meters per second that we squared. So that's 4 joules. And then it ended up going to 0. And so the slope of this line, again it's power, but that slope is going to be negative 4 joules. It's dropping by 4 joules across 1 second. So notice that that power is negative. That means also that confirms what the force versus displacement graph is showing us, that energy is being taken out of the system since we have a negative power. Okay, so that basically concludes 5.3 work energy theorem. Now, there is going to be another video, and it's about how to do the tutorials. And in that video, I get into the specifics of all of these different problems. Okay, so please watch that video because it'll be very informative. Okay, so we'll get into more details in the next video. Thank you.